All right, section 2.3, we're going to talk about other set operations and their properties, and in particular, we are going to look a little bit more at Venn diagrams. We just sort of barely introduced them this last time. Didn't really do much with them. We kind of looked at sort of a picture of what they might look like in a couple of cases, and that's about it. So today we're going to take a look at some set operations, and the first set operation we're going to look at is called set intersection. Set intersection is a set of elements common to both sets. So if you have two sets, let's say A and B, then the way that we talk about intersection is we use sort of that heel bone upside down, back from those Babylonians, okay? It kind of looks like an N, so intersection, you can kind of think of it that way. And intersection here means the exact same thing it does when two streets intersect. So when we talk about the intersection of two streets, what part of it is, what are we actually describing? The middle, right? So everybody pulls up to the intersection, but you don't stop in the middle of the intersection, right? That's the part that you're supposed to keep moving through. Okay, now intersection for what we're talking about is the idea of something being common to both sets. Okay, so something that they have in common. Now, in terms of notation, I want to show you what that looks like for our set notation that we dealt with last time. This would be the set of all x, such that x is in A. It doesn't look good. Let me try that again. And, that's a key word, x is in B. This feels a lot like when we did truth tables and we had the word and.
Wait, what's the sign between the x? Is that element of? Okay, I couldn't see it very well.
Yes, it's an element of. I don't know why my thing's not writing very cleanly today.
See it very well.
Yeah. Okay, that one's better, isn't it?
Okay. Yeah.
Just need to write them a little bit bigger. There we go. So x is an element of A and x is an element of B. All right, so when you think about intersection, so blended families are a fantastic description of both of these. So let me show you how this works. So let's say, and we're going to do an example later with a blended family situation, but when we're talking about the blended family, two people coming into a marriage and they each have kids already or whatever, and then they have a kid together, that kid's the intersection. It's what they both have in common, like DNA-wise, if you will, in my description here, okay? So that's the intersection. It's what they have in common between the two. Set union. This is the set of all of the elements in one set or the other or both. So you get all three sort of options. For a union, it actually looks like a U. That's very helpful, I think. And what we're looking at in terms of set notation for this one is that x, such that x is an element of A, or x is an element of B. Now, I'm not going to write or both, because or is not the exclusive or. It means either one or both. I mean, it means all three options. So when you see the word or, it means it could still be both of them. And we talked about this when we were talking about truth tables as well, the idea of something being or. If both statements were true and you put or between them, well, they're still true. Feels awkward, looks kind of strange, but it still works. So set union is the idea, again, of your blended family. And when you talk about a union, you're talking about everybody, right? You know, you get my kids and I get your kids, and we're all this one, you know, mixed up funny family now, right? But you get it all. So union is exactly what happens when you get married. It's the union. You get my debt and I get your money. No, that's not quite right. But something like that, right? There is some of that happens when you get married. So when they say, you know, I pronounce you husband and wife and the two shall become one, that's it. It's one union of all of it. So that's what a union is. Relative complement, sometimes called a difference, is a set of elements in one set that are not in the other. So this one actually looks like subtraction. Now, A and B don't have to necessarily sort of be inside of one another for this to happen. But if there's anything, and I'll draw pictures of these in a moment, if there's anything that overlaps, you exclude it. So let me do the notation for this, and then I'm going to draw you pictures of all these. So this is the set of elements where x is in A, and x is not an element of B. All right. So I'm going to draw the most general picture, which is the idea that the two sets overlap. So these are sets. It's a Venn diagram, set U, set A, set B. When you talk about the intersection of two sets, what do you think it would be talking about in this picture? The middle, right. It's talking about this piece right here. Just that little sort of fish shape or football shape in the middle. Okay, on this one, I want to draw the same kind of picture, although my space is not quite as big. I have set A and I have set B, and here's set U. What do you suppose the union would be in terms of this picture?
Part that's not.
You get that part. Yeah, and the middle. So we get set A, so this is my kids. This is set B, this is, the other person's kids, and then the set in the middle is the part we have together. Okay, yours, mine, and ours. There's a movie called that too. It is cute. Yeah, I like it. All right, so this is what we've got for this one. So the union, you get a whole bunch of stuff, right? Intersection is very exclusive. There's not much in it in practice, but the union, you get everything. The relative difference, or the relative complement down here, says that you're supposed to be in set A and not in set B. So what would that look like?
Just A where it doesn't.
Right. It's just this outer space out here, kind of like, the moon when it's not quite full. So you get just that outside piece. Now we're going to do an example with some people that there's a typo already in the problem. So let me fix the typo with you. Let me see where it is. Consider Mary, single mom of one child, Mark. Joe, single dad of two children, Jack and Jill. Mary and Joe get married. That's my typo. She does not marry her son, which would be bad. Mary and Joe get married. Together they have two more children, Ann and Andy. M is Mary's kids, J is Joe's kids, and we're going to find three things. The first one we're going to find is M intersect J. So what does that mean? The kids that they have together. So who would that be? Ann, whoops, and Andy, you betcha. Next one, we're going to do M union J. What would that mean? That's going to be all the kids, right? So we get Ann and Andy, but we also get Jack, Jill, and Joe? No, Mark. That's it. Ann, Andy, Jack, Jill, and Mark. And then we're going to do M, kind of looks like minus J. What would that mean? Yeah, it would be Mary's kids excluding the ones she has with Joe, right? So just Mark, exactly. All right. The next thing we're going to look at is called commutativity and associativity of these operations. So when we talk about commutativity, and we'll talk about it later in chapter 3, commutativity is the ability to switch or interchange things, okay? So you guys know it very comfortably with addition, right? 3 plus 5 is 5 plus 3. You can switch the order, doesn't change anything. Well, this is commutativity of set intersections and unions. So imagine if you had set A intersect B. Well, that's the same thing as B intersect A. Right? There's nothing different about that. And the same thing's true for the union. A union B. That's the same thing as B union A. Now, associativity has to do with how things are associated, okay? How they're grouped together. So we have to have at least 3 items in order to have a grouping, because we can't group 2 things together in different ways. It's just one way to do that. So when we're talking about this kind of grouping, we're talking about associativity, we're talking about grouping. So something like this. And the question being, how are they grouped? Well, we could group the first 2 together, or we could group the second two together and it won't make any difference. It'll be the same. So this one's written for union, but it also works for intersection. Notice the notation is the same. It's all unions or all intersections in this one. Okay, so you can put the parentheses in and group things in whatever way makes the most sense to begin with. And then the last one is the idea of distribution over set union. So you know what distribution probably is. You've thought about it before, at least with numbers. It's the idea of taking multiplication and sort of, distributing through the addition or subtraction of two things. You do it with algebra. Well, it works the same way here. If I have A intersect B union C, I can take this and distribute across. So I can do A intersect B. I can do A intersect C. And what do you suppose goes between them?
Union.
A union, because there was a union here to start with. So this is a distribution of intersection over union. And all of these work for all sets A, B, and C. All of the above can be done for any set. There's nothing special about the way those sets are related. They don't have to be subsets of each other. They don't have to be completely disconnected. It works for any of them, any of those possibilities. All right, the next thing we're going to look at is the cardinal number property formula. So it says that if I take, and I'll justify for you why this is true, the picture in a moment. If I want to know the number of items in the union of two different sets, what I do is I take the number of items in one set A, number of items in the other set B, and I subtract the number of items in their intersection. Now I want to show you why it's subtraction, because you might be thinking, well, why isn't it addition? Well, take a look. So here's my sets A and B. And let's imagine what we do. If I want to know the number of items in set A, I would count everything inside of circle A, including the intersection, right? And then if I wanted to know the number of items inside of circle B, I would count everything inside of circle B, including the intersection. And what happened? Yeah, the intersection got counted twice. It got counted when I counted set A, and it got counted when I counted set B. Right, this is what would happen if Mary and Mark were counting their kids over there, or Mary and Joe were counting their kids over there. If Mary says, I have 3 kids, and Joe says, I have 4 kids, they do not have 7 kids together, right? Right? Or, well, they do have 7 kids together. I didn't say that right. What did I want? Yeah, they didn't have 7 kids together. They had 5 kids together, didn't they? It was 5, yeah. Yeah, we can't just add the number of kids, because some of them got counted twice, Ann and Andy, yeah? That's what's happening here. And so when you're doing the counting, you have to remove one of the double counts in order for it to actually be the right value when you're done. The final set operation in this section is called Cartesian product. So the Cartesian product is a set of all ordered pairs, such as the first component comes from the first set and the second from the second. Let me show you what this looks like. First of all, product looks like multiplication. So this looks like A cross B. And it says this is a set of ordered pairs, so we will call our ordered pairs A, B, like XY in the XY plane, okay? But it has to be the case that little a comes from set A and little b comes from set B. And this starts to look an awful like the problem, Kayla, that you asked me about up here, right? Kind of like I plus j, except that we're not going to add them. We're going to leave them written as ordered pairs. Okay, so it feels something like that. So I'm going to do an example of how this works so you can just see it. Let's say we're going to let A be the set X, Y, and we're going to let B be the set 1, 2, 3. Then if we're finding A cross B, it means that I'm going to have elements from A as the first part of the ordered pair, so maybe like X, paired with an element from B, maybe like 1. So this element as an ordered pair X1 would be part of the Cartesian product. But x didn't have to be paired with 1. It could have been paired with 2. Or it could have been paired with 3. But again, x wasn't the only thing inside of set A. There was also a y. So y could have been paired with 1, or 2, or 3. So I get how many points? 6 points. So take a look at this, just so that you're aware of it. I don't think I tell it to you later, so I think I'll make a mention of it now. A real quick check step to make sure that you found the right number of elements is taking a look at the number of elements in this Cartesian product. How many ordered pairs did we just get? 6, right? You can count them, there's 6. How many values are there in set A? 2. How many elements are there in set B? 3. And if we've done this right, when we multiply these number of elements up here, these should match. We're doing it from a very different perspective, right? And we're counting different things. One of the places we're counting actual ordered pairs, right? We counted down here. 1, 2, 3, 4, 5, 6. And over here we counted these 2 and we counted these 3 and then we multiplied the 2 times 3 together. But if we've done the problem right, we should get the same number either way. Okay? Any questions on that one? Okay. I want to do, we're going to stop right there. All right.